We're in my office at the University of Geneva. I'm a professor at the Department of Quantum Matter Physics. And I know it doesn't quite look physicsy with the snake here in the terrarium and the turtles here in the tank, but we are at the École de Physique, and my laboratories where we actually study materials with scanning probe microscopy are in the basement. As a materials physicist, one of my friends once said that what we do is basically the relationship between structure and properties. I want to know what happens to these structure-property relationships when you look at very small regions of materials. Because sometimes, especially when you look at very small length scales, you can find properties that are very different than what you think of as the bulk of the material. And some of those properties are not only very fundamentally interesting, but they're also very useful for application. In materials, for example, like the magnets on your fridge, we have a north and south that's oriented in a particular way. So when they orient in different directions in different parts of the samples, we call those regions domains, and then the interfaces between them are domain walls. These tiny, tiny regions, because they're only, let's say, a nanometer wide, can have very, very localized and very different properties from what's around them. So usually the samples we look at are those electric materials, we call them ferroelectrics, and they're insulators. But the domain walls are locally like little conducting wires. They can actually carry electricity. So you can already imagine, okay, that might be a useful device where you have a local interconnect that's automatically really tiny. So there's already worldwide, in the last 20 years, a very big push for what's called domain wall nanoelectronics. Lots of big words. What it means is electronics on a very, very small scale, but using these domain walls as, for instance, elements like diodes or little ratchets or just conductors in an otherwise insulating background. And so what we can build is, if you're familiar with devices that are based on transistors or devices that use logic gates or so on, we can make them in miniature using those domain walls as the foundational elements. Well, we like explaining our type of microscopy generally with these everyday, very classical example, scanning like a blind person across the surface. But in fact, the quantum physics that underpins this is present in the very nature of the measurement. We're looking at things that are a few nanometers or even sub-nanometer in size, and the interactions between a tiny tip that is itself a few tens of nanometers and the surface are happening at a quantum level. And the properties we're looking at, in particular the properties of interfaces, which arise as a very subtle interaction between the quantum aspects of the material underlying them, are in fact primordial to what we get as the information. What I really love about doing the kind of research that we do on materials is that feeling every once in a while you are doing a measurement and you realize you're just looking at something that nobody's seen yet. That kind of level of excitement when you find something, and even more when you understand it, because half the time we're experimentalists, so we see something and the usual response is, oh, that's interesting,